to this Desmos activity. All right, so we're going to apply the fundamental theorem of calculus, or the evaluation theorem. Since this is section 5.3, we should be calling it the evaluation theorem, but ultimately it's going to be the fundamental theorem. So I need to find an antiderivative of the integrand right here, and then I'll plug in 1 and 0 and then subtract. All right, so an antiderivative of x is going to be 1/2 x squared. Remember, root x is x to the 1/2 power. So when I add 1 to 1/2, I get 3/2. And when I divide by 3/2, I get 2/3. So it's 2/3 x to the 3/2. And then evaluate that from 0 to 1. And so that means I need to plug in 1, which gives me 1/2 plus 2/3. Plug in 0, which gives me 0. And so it's just a half, which you can simplify, but I'm not going to. All right, here's example number 2. Again, we're just applying the fundamental theorem. An antiderivative of 3x squared is going to be just x cubed, and then plus 1/2 x squared minus 2x. And then from 0 to 3. The nice thing about having 0 as one of our limits of integration is that these expressions all come out to be 0. Not all expressions do that, of course, but these do, so that works out nice. So 3 cubed is 27 plus 3 squared times 1/2, which is just 9/2 minus 6. And then plug in 0, and we get 0. And so that's our answer. I'm not going to take the time to simplify the arithmetic. You can on your own. For example number 3, this is just the integral of the constant 3 from 2 to 7. Now you could do this geometrically, and remember that this represents just, a horizontal line at 3, y equals 3, pretend that's horizontal, from 2 to 7, and just find the area, of this region. So it's just, 3 times 5, or 15. But if you want to use the fundamental theorem, then we could find an antiderivative, 3x, and then evaluate this from 2 to 7. Plugging in 7, we get 21. Plugging in 2, we get 6, so we get 15. So geometry and the fundamental theorem agree on their answer. All right, so what do we have here for number 4? So we need to find an antiderivative of 8y squared. That's going to be 8/3 y cubed. So we're going to add 1 to the exponent, divide by that new exponent. That's how we got the 8/3. And then the antiderivative of sine, well, the derivative of cosine is negative sine, and this is positive. So I'm going to need the opposite here. This is cosine, again, derivative of cosine is negative sine. I need to multiply by the negative to make this a positive over here. And then I need to evaluate this from negative pi over 2 to pi over 2. The nice thing is, for this example, is if I plug in pi over 2 to cosine, I get 0. And I plug in negative pi over 2 to cosine, I get 0. So this is going to be 8/3 pi over 2 cubed minus 0, and then minus, and then we're going to have 8/3 negative pi over 2 cubed, again minus 0. And then from here, I'll do a little bit of simplifying. So this is going to be 8 pi cubed over 2 cubed is 8 times 3 is 24. And then over here, when I cube the negative pi, it's going to become negative. And so subtracting the negative makes it positive. And then everything else works out to be exactly the same, like this. And then, we could go 16 pi cubed over 24. Now 8 goes into 16 twice and goes into 24 3 times. So there's our answer for. All right, so here's number 5. And so fundamental theorem, we're going to get 1/2 u squared. And for the 1 over u, you can think of this as u to the negative 2. And so when you go to find the antiderivative, you're going to add 1, which makes this u to the negative 1, and then divide by the negative 1. So it's really just negative 1 over u, but we're subtracting, so we should have a plus 1 over u. Excuse my dog in the background. From negative 2 to negative 1. And then when I plug in negative 1, Well, negative 1 squared is going to be just 1, so you get 1 half. I plug in negative 1 here, minus 1. And if I plug in negative 2, well, I'm going to get 4, and half of 4 is 2. Plug in negative 2 here, I'm going to get a negative 1 half, so minus 1 half. And then at that point, it's just arithmetic, which you can do on your own. Now for number 6 here, we're getting into the indefinite integrals. There are no limits of integration. So all we're doing is finding the most general antiderivative. And so the key mistake I see students make on this is to forget the constant of integration. So let's try not to do that. So add 1 to the exponent, divide by that new exponent, or multiply by its reciprocal. 1/4 x to the 4th plus 2x plus c. There's your answer for number 6. All right, so we're finding the most general antiderivative of secant squared x minus sine of x. We should all know that the derivative of tangent gives us secant squared x, so this is going to be tangent of x. And the derivative of cosine gives us negative sine, so this is going to be plus cosine of x, and then plus a big C. You can always test your answer by taking the derivative, and so my dog is agreeing with me here. That's what the barks are for. Those are barks of affirmation. But we can test this out. So the derivative of tangent is secant squared x minus derivative of cosine is negative sine of x. Derivative of constant is 0. And notice that the result here is exactly the same as the result here. And if that didn't work out, then we would know we had a mistake. Now for number 8, you have to be careful not to start taking the antiderivative of the terms separately here in the product, because we don't have a rule that allows us to separate products for antiderivatives. And if you do that, then you're just going to be in error. Luckily, you don't know an antiderivative of secant anyways, because we haven't worked out something like that. That's for a later time. So you'd get stuck there if you were trying to do that. What you want to do is sharpen the axe. Okay, let's do a little bit of algebra here. Let's distribute the secant of theta. So secant theta tangent theta minus secant squared d theta. All right, so after we do that distribution there, we should be able to recognize that we know the derivative of secant theta is going to give me the secant theta tangent theta. So there's that, and the derivative of tangent will give us secant squared. So that's our secant theta minus tangent theta. Of course, we need our plus c to be correct. For number 9, we have this expression here. And again, we don't have a rule. Similarly to the previous example, we don't have a rule for a quotient. So you can't take the derivative of the numerator and the derivative of the denominator and divide and get a correct result. You need to do some algebra first, okay? So I'm going to separate the fractions here. So I'll do this longer than I care to do it normally, but just so everyone can see what's going on. I can separate the fractions like this, and then I could further rewrite this as the integral of 1 plus 1 over x squared with respect. What is that shape? Trying to give me a trapezoid there. And so antiderivative of 1 with respect to x is x. And then we're going to minus 1 over x. Hopefully you can see that from an earlier example that we worked through. Plus a constant. If you can't, I'll pause for a moment. You should pause the video and work it out on your own, but just to demonstrate that, remember this is x to the negative 2, as we said in an earlier example. So when I go to take the antiderivative, I'm going to add 1 and get x to the negative 1, and then divide by negative 1, so that's why we have our negative here, and x to the negative 1 is 1 over x. Last but not least for this example, the antiderivative of 2 to the x times the natural log of 2 with respect to x. This one should be pretty straightforward. You should recognize this as 2 to the power of x plus a constant. All right, I hope that was helpful. Go study.